So today we're going to continue on with the gases, and there's this strange device called a manometer or a manometer, the measure of a man. I have never personally seen one of these things, and I know that we've never had one in the classroom, whether here or Avon, because it involves pouring mercury into the thing, so that's out. But here's the concept behind it. And again, whether it's real or imaginary, hopefully it's imaginary because I've been on this rock for a while. I just haven't seen one. But you evacuate the gas, you pour the mercury in there, and what happens is you tilt this thing until all the mercury pours. So you got to tilt it this way until all the mercury falls into this portion of the tube. And then you steady it or right the manometer so that the U-tube is actually facing down. If there's a vacuum on this side, we obviously know there's a vacuum on this side. The levels of the mercury inside and out, or on both sides of this, are going to be the same. You open up the valve, introduce a gas, and then the gas, and you can see the little collisions down there hitting on the mercury itself, will actually force the mercury down and the other side up. Now again, to make this more complicated than it really needs to be, the difference in the height gives us a pressure reading. So, hypothetically speaking, if we introduced the gas into this closed-ended manometer and the height of the mercury was 165 millimeters, what is the pressure in millimeters of mercury?
165.
165. Very good. It's just that. Yeah. So here versus here. So we start off level. We introduce the gas, and then the gas pushes down the mercury here, but elevates it here. So the level in the height is 165 millimeters. All right, so today we're going to talk about one of the four laws that we're going to be dealing with. The first one is Dalton's law of partial pressures. The next two we're going to talk about tomorrow is Charles' law, and then Doyle's law. And then we're going to talk about Avogadro's principle on Monday. The first one, partial pressures. It's an easy concept, but for whatever reason, students like to make this a lot harder than it needs to be. Kind of like that last example with the difference in the height of the millimeters of mercury. Don't make it harder than it needs to be. Think about what partial pressure means. Here's an example. Let me scroll down a little bit so we have some room to draw. In the atmosphere, okay, here, the big P actually represents pressure. So if I have my atmospheric pressure, what we're experiencing right now, there are like three major components of gas. The first one being, what's the most abundant thing in the air? Nitrogen, very good. And it's around, we'll say 80%. Okay, it's probably a little less than that, but it's close to that. What's the next one? Oxygen, thank goodness. And we'll say it's around, just for kicks and giggles, 18%. And then the last one, carbon dioxide, and we'll say around 2%. Okay. Now, if you're over by Cade, there might be a little bit of methane, but yeah, we're not going to consider that. So, all right. So when we talk about the atmospheric pressure, we know that we have, at least for this sample of gas, three major gases in here, or three gases. Now let's just pretend that these are the only gases that are actually present in the atmosphere. They're not, but these are the big ones. So if I know that I have, say, for example, 1 atmosphere of pressure, okay, as my total pressure, and we talked yesterday that if you have the same number of particles at the same temperature and the same pressure, well, not pressure, not in this case. Oh yeah, we did talk about pressure. It would occupy the same volume. Now here's my thing. Pressures are equal if you have the same number of particles for any gas. If I said we had 1 atmosphere of pressure for our atmospheric pressure, what would you guess is the pressure due to nitrogen? Not 80, but 0.8, right? So it's 80%. So if we have 1, it's 80% of 1. Okay, and then if we look at oxygen, it makes up 18%, so it would be 0.18, and this would be 0.02. Very good. Not 0.2 because that's 20. That's the concept. Don't make it harder than it needs to be. Okay. Now, some of you are like, well, yeah, we're not going to make it harder than it needs to be until you look at a different type of problem. So, in summary, what that's saying is we're going to make sure, and here's an example. Here I have this is Dalton's law of partial pressures, and that equation would be given, or that expression would be given to you. You just have to know how to use it. That the sum of the parts equal the whole. Right? Okay. Does everybody have the blanks up to this point? Okay. Now here's an example. Okay. Here I have hydrogen gas in this container. Here I have helium gas in the middle container. In the last container I have both of the gases mixed together. In this, we have the gases are at the same temperature, we have the same volume, but they obviously have different pressures. If I look at, say, this pressure here due to the hydrogen and this pressure here due to the helium, what do you think the total pressure if I combine those two gases are? Close, 10.1. You just add them up. And if you need to, you can use a calculator. Because the volume remains the same, so the pressure is going to go up. Now, here's how we find out what our percentages are. Again, since these gases behave in the same way, at the same volume and at the same temperature, if we have equal numbers of moles, then we'll have equal pressures. But we don't have equal numbers of moles. We actually have different numbers of moles. So if I want to find out what the partial pressure, if I had, say, this only to look at, here's how I would figure it out. I'd find out how many moles of helium I have. I would find out how many moles of hydrogen I have. Add those two together. So that gives me my total number of moles. I know my total pressure. So there's my total pressure. And it's equal to, in this case, 10.1 atmospheres. If I wanted to find out what the pressure due to hydrogen was, then I would say, okay, hydrogen is 0.6 moles of how many total moles of gas? 210. That gives me, quote unquote, a fraction or percentage if you wanted to. And then you'd multiply that times the total pressure, and that would give you this pressure right there. Okay. So sometimes you have to do a little more of the math other than just looking at the parts. And we do have a practice problem like this. So, but the nice thing is when we look at the gases, as long as they're at the same temperature and we're looking at the same similar volume, then we can actually do some really easy calculations that are for Dalton here. Okay. All right, here's another scenario. Here we have a bottle, okay, and we can actually fill this whole thing up with water if we're really careful. And if you tilt this up, let's pretend that this was completely filled with water. We'll do a lab like this, not next week, but either the following week or two after that, before spring break. We're going to bubble a gas through here, and what's going to happen is as we bubble this gas through, we're going to build up the pressure of that gas, and it's going to force the water to go down. Yeah. And as the pressure increases, then the level of the water in the bottle will actually drop. The most important part is when the level inside and the level outside are the same. Anybody tell me why that's important? Okay. Here's why. If we know what the atmospheric pressure is outside the bottle and the level inside and outside are the same, what can we say about the pressure inside? It's exactly the same. Okay. That we know for sure. If the level is not the same inside and out, it's difficult to calculate that. And we won't do those types of calculations in here or in AP. Let's say that the level, okay, here, looking at the level of the water in this bottle, is the pressure greater or less than the atmospheric in the bottle here on the left? Less than. Why? So there's not as much gas, which means there's not enough pressure to push that water down. What if we said the level of the water was here, in the bottle? It'd be greater than the atmospheric pressure because the level is below. So when we do that lab in 2 or 3 weeks, we want to make sure that we're adding enough gas so that the level inside and outside is the same so that we know exactly what the pressure is inside. Now, here's the other component. So that's a big concept. The other concept is, in this problem here, we're actually bubbling hydrogen gas through here. So in here we have hydrogen gas. But also, since we're looking at water, water evaporates rather easily. Now, it doesn't like quickly, but there is some water vapor. And so also, the gas that's in here is some water gas. If you have, say, you're bubbling a gas through water, you're not only going to have the gas that you're collecting, but you're also going to have the gas of water. There's a term that goes with this. Okay? Now, I apologize in advance for some of you who are pretty sensitive about this. It's called a wet gas. Okay? Which means that there's water vapor present, or that there's gas that's wet. Okay? So we have hydrogen. If you are looking at a dry gas, okay, what does that mean? We ignore the water. Okay. So wet gas means that we have to look at the water because it is contributing to pressure. If I say calculate the dry gas, all we're looking at is the hydrogen, okay, which is a lot easier to calculate than with both the water and the gas that we're collecting. Okay, so you'll hear me use that term because that term is used quite a bit in AP. They like talking about wet gases, and it's not a bad day. Hopefully. All right, so here's our first example of two. All right, so here we have a scenario here. It says you collect a sample of oxygen gas by water displacement method, just like the bottle that we had just above here. If the atmospheric pressure is 99.4, so let me write that down. So the atmospheric pressure is 99.4 kilopascals. And the water vapor pressure in the bottle, so water, is 4.5 kPa. Again, I'm just writing the information down. Question is, it asks, what is the partial pressure of the oxygen gas? Now here's how we write this out. So we've got our total pressure is equal to our, not our total pressure, our atmosphere. Whoops. So our atmospheric pressure in this case, because again, when we're looking at the bottle, okay, we want to make sure the pressure outside is equal to the inside, so we can use that as an equal here, is equal to our pressure of, what is it, oxygen or hydrogen? Oxygen, my bad. And the water. Looking at that setup, does this problem look difficult? Well, hey. Okay. So what we need to do is we need to isolate for the oxygen. So that means subtract water on both sides. So now my equation looks like this. My oxygen is equal to the atmospheric pressure minus the water. And then we plug our numbers in, which is 99.4 minus 4.5. And get a number. Don't make this harder than it needs to be. Okay. Now, the question that you're probably thinking about, what do I have to show to get full credit? What I have in kind of bubbled in, boxed in, whatever that is, with your answer, of course. Okay. That's the minimum that I would want to see. Everything outside of that is for you to do. Okay, so again, show me what you're looking for, show me what was given, the variables rearranged, and of course the numbers plugged in. It's an easy problem. Okay. Questions about that? Anybody get a number there? Okay. 94.9. Good? Yeah. Sure this is chemistry? All right, the next one is a little more adventurous. Okay. All right, here it says a mixture of 84.06 grams of nitrogen and 83.8 grams of krypton. We have grams. Whenever we have grams, we need to convert to moles. Very good. Now, here's the reason why. Because if I said that we had 84 grams of nitrogen and 83 grams of krypton, we said grams were equal, we would just say, oh, yeah, it's approximately 50%. These are not 50%. However, if I had 1 mole of this gas and 1 mole of that gas, now we're looking at equal things. All right. So whenever you see grams, get it to moles. Don't even think about it. Get it to moles. All right. And then the question says that the total pressure of these two gases is 280 kilopascals. It wants to know what is the partial pressure of each of these gases. All right. So again, we're looking for the total pressure, and we're going to combine these two together. So nitrogen and what is it, krypton? Okay. Now, so that's what we're looking for. We're going to find out what each of these happen to be. Okay? That's what the question's asking. So first things first, let's make sure that we actually find out how many moles of each we have. So nitrogen, we have 84.06 grams of nitrogen. And remember, gen means that we're looking at a diatomic. If it doesn't end in gen or ine, then you're not looking at the diatomic. Okay? So we need to convert that into moles. And the molar mass for that is 2 times 14.01. Okay, we'll get a number of moles there. And that is 3. How nice. And that's of nitrogen. And then we'll do the same thing for the krypton. So we have 83.8 grams of, and how do you write krypton? KR or KR2? KR, very good, since there's no gen or ine at the end of that. And it's a noble gas. And 1 mole of krypton, yes, I made this problem, and I made it really easy. 1 mole of it is 83.8 grams, so that equals 1 mole of krypton. Now, here's the thing. Again, gases under the same conditions behave in the same way. So if I have 3 times as much nitrogen as I do krypton, what can I safely say about the pressure exerted by nitrogen? Is it equal? Is it greater? By how much? 3 times. Just that easy. All right, so knowing that should help you out on this. Now, what we want to do is we need to find out what that percent of nitrogen gas is and what the percent of krypton gas is. So we're going to take the total number of moles, add those together, so we get 4 moles of gas. Okay, because again, looking at the example that I gave you with the hydrogen and the helium, mix those 2 gases together, they're not going to form anything new. So now that we have our total moles of gas, now I want to find out what is the partial pressure for each of these. So here's how I do it. Ask yourself, how many moles of the total gas do we have that's due to nitrogen? We have 3. How many total moles of gas do we have? 4. So nitrogen makes up 3/4 of the total sample of gas. And whenever we do this, we want to multiply our percentage by the total pressure, which in this case is 280 kilopascals. So when I work that out, I get hopefully 210. So nitrogen has a pressure of 210. Now there's 2 ways that you could find the krypton, but I'm going to do it the same way just to be consistent here. So finding the krypton, do the same thing, where krypton is, how many total moles do we have? 1, good. And we have 4 total moles of gas. So here's our partial pressure due to that. And then that should equal 70 kilopascals. And as we stated earlier, do we have 3 times as much nitrogen as we do, I'm sorry, pressure-wise, 3 times as much as the krypton? Yeah. Now, here's the kicker. if you were focusing solely on the grams itself, and you're like, oh yeah, we got the same mass, then it's going to have the same type of pressure, that's a dangerous path to go down. So always change your grams into moles, especially when we're working with gases, so you can find out how many total moles of gas you have, so that we can get either a fraction or a percentage. Sometimes I'll give you the percentage. If I'm giving you the percentage, don't go crazy and think about, oh yeah, empirical formulas. Take that percentage, find out how many grams you have, and then find the. I already did the work for you. If I'm giving you a percentage, that is like the fraction that I just gave you. All right, and then just multiply that times the total pressure. And then if you needed to, for whatever reason, you wanted to check and make sure that those actually added up to each other. Again, going over and above, I would never require this. But if you needed to, just as a check, make sure that that actually does add up to the total. Sound good? All right. Questions on that? And again, this one's a little more involved than the last one where I gave you the pressures. If I'm giving you the pressures of each gas, don't go crazy and try to find out what those new pressures are. If I'm giving you pressures, I probably am looking for an unknown. Yes, Lo? I know. If you're ever given grams of a gas, get it to moles, first and foremost. You're gonna, once you have your total moles of gas, add them up. Right. So we want to look at how many total moles of gas we have in the sample, just like with our image that we had back here, kind of blurred there. So we had our 0.6 moles of hydrogen, 1.5 moles of helium. Mix them together, we have total moles of 210, or 2.1, sorry. And then, so the pressures are additive, so we can find out what our partial pressure to each is. If was given.
So then after you find the moles and you take the mole of nitrogen, let's say it's 3 over 4 moles of gas, which is the whole thing, you multiply it by 280 kilopascals and get that add them together.
This you don't have to do, but it's a check. If for whatever reason you need to have that security blanket, that's fine. But these better add up to the total when you get done. Or if you have multiple gases, make sure they all add up.
And so for the answer, would you just circle 210 and 70?
Yeah. Yeah. And sadly, though, the green and the red I would need to see, minimum. The blue, that's whatever you need if you want to do that. Okay. Sound good? All right, let me do some explaining on the homework here. You good, Han? Okay. It's like before I zap this all. All right, on questions 2A and 2B, these are the questions I want you to ponder. Okay, these are going to drive you crazy because I'm requiring you to think a little bit here, and I know that's not something that we like to do. And again, there is no wrong answer as long as your explanation justifies what you're saying here. These two questions are different, okay, so it doesn't come easily at first. Then 2C, 2D, and 2E, sadly, are just plug and chug calculations. But A and B, I'm getting you to try to think here a little bit. I know. Okay. Any other questions on today's stuff? Pretty fun? Super.